about water in foods, which has been some part of my research over the years. I talk about water and mobility, and you may think about the water molecules are almost like the little water pipes there in the cars that you go in the traffic jam in Bangkok. And they are really quite more work. But so this slide is just to start to talk a bit about the importance of the topic, because water is a very important part of our food. But it always interacts with the structures, and it has many functions in the food. I can certainly not go through them all, but we can see many processes and also the properties of water and the food solids that find together in many of these processes, up to the era where we have developments in these drying and other dehydration processes, glass transition, and then also the cryostabilization and overall food material science towards these days. So there's a lot of research that has done over the years, and we often do not really look at the water itself that much. What I saw there is a phase diagram from Professor Emeritus. He published quite a lot about water in as a substance, and it has properties that are non-solid, supercooled liquid water that goes to very low temperatures, and it shows also transition, and even different types of that. What I also wanted you to recognize at the start of my talk is the Roos law, which is very important in that regard, that we are looking at water as a solvent, and it always plays some role with the other components that are in the food as well. So in that regard, over the years, there's a number of different cascade diagrams or supplemented phase diagrams that have been developed to understand more in detail what happens in water solid systems, particularly the substances that interact with hydrogen bonding with water, so they are polar substances. And from the 60s to 80s, they showed some contributors. There was a young student in the 60s, Rasmussen, who looked at the sugar solutions, and then Felix Franks, who is a well-known guru of the water as such. He was in his time, and then some of the developments that happened in the 80s by David and Roos today that related to vitrification, also the overall interactions of water and water as a plasticizer in foods. So, if we look at freezing of water in food makers, we could look at also the work that was carried out in the early 70s by Professor Charles King in Berkeley, and they did quite a lot of fundamental work in understanding how the viscosity of a solution changed when it was getting frozen, and they described actually that there's an amorphous phase form and that it becomes stiff at some point. So there was ice formation because of thermodynamics, and then the ice formation continues even below eutectic temperature. So not the solvent crystallizing quite often, because sugar crystallization is a slow process. The water molecules crystallize much easier, but very slowly also if the viscosity is very, very strong. So then the system is retarded, and what has been done is some of my early work here on strawberry substance, because we were trying to see how freezing happens in real systems, and we used the differential scanning calorimeter that is quite normally used to look at dynamic changes in samples. So we could see that if we have this water, we have the fast transition moving to higher temperatures, the more water is frozen, freezing, or if the water activity of the system goes higher, the fast transition upward at a higher temperature. So we could actually then start to look at what is the effect of the water content on ice formation in these substances. So based on that, we could then look at a number of different phenomena, and we came in the 90s to establish the sucrose diagram that is shown here with number of points on fast transition, etc. in state diagram form. What we were showing there was that the temperature range where we can observe maximum freezing is actually very narrow, and that is because of the retarded movement of water molecules, and also the level of hydrogen bonding that happens between water molecules and the sugar molecules. So that then becomes a factor that controls the rate of freezing. And then I had a chance to work with Professor who was a person from MIT with a lot of experience on food material science over the years, and also he was working closely with the Larusa, who you may also know in the area of water and foods. So then that will have also contributed to the drier side of materials. So we are actually, like in the strawberry diagram earlier, showing time dependence and the fast transition movement in water content. We would also see that there are other contributors in dry foods that control reaction kinetics. So we would be able then to combine the information of the material property in the presence of water and different water levels to control. And well-known food stability math is also shown here that combines together the water and the fast transition. And the food polymer science proposed by Harry Levin was late contributing that time quite a lot of to this water motility picture of those things. There's a picture with Harry and Louis and the Larusa. I remember the open line to show that in many contexts because they would ask which is the water moving because of the water or the gas. So you may think about that. But anyhow, they were working on the fast transition and having Louis on the fast transition. But we can see in the stability map an area where the material property is very strongly dependent on the water content, whether you measure it as a quantity or as an activity scale. So these things then come together also in sorption isotherms, etc., where we could analyze them in terms of quantity of water related to the amount of water. The PET theory is well used quite often. Here we only show that the parameters affect what it is in terms of quantity and how the material properties may affect that, but also that there's monomer content that may be not that easy to understand or actually perhaps it doesn't exist, but it's just a concept that relates to some isotherms. Also in the GAP isotherm, which is shown here, because it is only an extension of the PET theory, but we can have different frequencies of curves and describe the water relationship with the material properties. I don't discuss this in detail how these relate together. I only show these as a tool because if we like to establish very detailed state diagrams and phase diagrams and related food properties and the stabilities and the reaction affinities, quite often we need to understand what is the relationship of the quantity and the activity. And if we can do that, we can even use combined materials to derive the properties at different contexts. So these are important background information. There has been always discussion about whether the monopoly exists, and I think pretty much the same as Nicolet has said in this statement that does it really exist. The cryostabilization is another thing. We don't usually think too much about the systems too much about the water content, water activity relationship in cryostabilization. But I will show you that they actually can be used in somewhat combined as well. Cryostabilization basically means that you look at the frozen water in the food, and if you can solidify water as crystals, part of the water remaining unfrozen, and then the solids becoming a class with that water environment. You may assume that state is quite stable. You don't expect many physical changes taking place, and also the chemical reactions are retarded. So that's why cryostabilization term was used by Adelaide to say about the This diagram goes back to the unfrozen water. Doesn't exist. We always say unfrozen water because in these systems, water molecules are either frozen or parts of the crystals, they are frozen or they are unfrozen. But all water molecules would be able to freeze. So that's why I always emphasize that unfreezable water does not exist. But you can see in many literature that they would mention unfreezable water. How much water can crystallize is open question. And here is one literature diagram about water molecules. There's a limited number of water molecules that has to be exceeded before ice can even form. Then if we have interactions of sugar and water molecules or some other polymers, etc., that are finding the water, then these numbers vary. And we have shown that there's about 2.5 molecules of water to each supermolecule. Then I mentioned already the time being an important factor, because if we start to talk about viscosity and the rate of reactions, etc., we have to consider how long does it take for some system to stabilize or become metastable. We did a number of experiments showing that if we give time to water molecules to move, even in a very stiff situation, they can form crystals unless it's stopped by something else. And I would say that they are stopped at some point because of hydrogen bonding becoming stronger than binding to the ice crystals. And that's why we can have maximum isomerization over being around 20% water versus 80% solids. And that was the outcome of these measurements that are shown here, points where water crystallization was looked at different supermolecules, and this is a kind of schematic diagram showing what the water molecules may be very solution with ice crystals and supermolecules and the passing to that quite exact quantity. And based on that information, we did the state diagrams for sugar type of sucrose, etc. We have very similar systems, and we defined two things that is in frozen system. P prime, that means that above that temperature, there is always dilution because nothing of ions. And then P sub C prime, which is only one condition where the gas transition matches the maximally is concentrated state. If you have more water, you can still get glass, but you have to cool it very rapidly to low temperature so that it solidifies at the different temperature. And that is because of the competition of the cooling rate and the ice molecules trying to build in. We can also then, as I said, sorption isotopes, we can obtain data here, and then solutions we can obtain data here, and we can establish quite a complete relationship between the water and the water content. So in kinetic terms, this has been related to stability. This is all the information from researchers on sucrose and looking at the humidity, where crystallization time taking a year or two, but something was happening very slowly. And those things we can see nowadays more rapidly in dynamic water sorptions, where we can get actually different types of curves depending on rates we use. And then we can look at also static sorption isotopes that we can establish. So those are often different. And there's the pattern. A fractional water sorption is also an important thing. This is looking at water in maltodextrin systems with our lactose systems. This is data from, let's say, others was here as well, from the PhD at the time. And that shows that you actually can derive from this data how much water is in each component. And that sort of thing is quite important if you're looking at drying or freezing and other properties of materials with different components. You can have sugar mixtures, or you can have water mixtures of protein and sugars and so on, that you can then start to figure out, for example, in the frozen material, how much of the water gets frozen or how much you could have. Or you can have a full isotope of a crystallized uncrystallized lactose, which has also data from areas where normally lactose would not stay in non-crystalline. Then, important parts of this time dependence is the moderate relaxation time. So we have to go into the time. So the WLF equation is fundamental there, which has been often used over science. It's a model that has actually a number of different types of curves depending on the constants. And the constants are according to this green line here in the application. What we could do in that regard is to see how the material softens about the glass transition. And that is very important in controlling stability of dry materials or the vibration process, because that tells you how you can keep it not sticky on these other particles. So applied that sort of approach to establish mixtures of materials, and we could say different temperature of the glass transition that we call the strength parameter. And here, for example, data on the alloys and whey proteins and how the composition changes this substance of transition. And that one student from the next one which did nice work on honey powder. And I mentioned the low temperatures, whey proteins actually they find water, proteins find some water. We can measure that water to make a separate class that is shown here in dynamic mechanical measurements that derive how that happens in different water. So water is actually an antiplasticization there. And then we could do complex realistic diagrams that explain water, sugar, and protein systems quite clearly, how they depend on the amount of water, and we could see also what is in protein structures, the water that can breathe. So, in conclusions, there's a number of points. But anyhow, I would emphasize the rate of water contributing or its movement contributing to reaction kinetics, physical stability, and so on. And then cryopreservation, drying processes, and multicomponent things that are always important in the food area, and the strength parameter that provides some information on how to control the substance and the transition. So thank you very much for listening, and we'll have some other people who have contributed to the content side.
Thank you, Professor, for elaborating what are your calibration of the particular water and its relation to